This video lecture is about one of the first problems that we really encounter in doing atomic or quantum physics. And one of the first problems, or easiest problems to solve using the Schrodinger equation. I'm not going to go into really where the Schrodinger equation comes from too much, but maybe we can talk about that in a different place. But let me go ahead and share my screen. I'm going to do most of this writing by hand. I just find it's easier that way. So one thing that comes up when we deal with quantum physics is the idea of wave-particle duality, where photons are particles of light, but light still has a frequency. Same goes for electrons. Normally we think of electrons as particles, but they can have a wavelength. And when we talk about quantum particles, wave particles, objects, there are two equations that are really fundamental. And the first is the energy of a photon, or photon energy type of equation. I guess I could call it energy frequency relation. E equals hf. Now, I could write this in terms of an angular frequency, 2 pi times the frequency. And I could write it as h bar omega. So omega is the angular frequency, 2 pi times the frequency in hertz. This h with a bar through it is a shorthand notation for h over 2 pi, right? And h, again, is Planck's constant, 6.63 times 10 to the negative 34 joules times seconds. The other equation that comes into play is kind of the momentum wavelength relationship, which is true both for photons and particles, or electrons, that the momentum is equal to Planck's constant over the wavelength. I can define a wave number, k equals 2 pi over lambda, and this is often then written as p equals h bar k. Now, the problem we're going to talk about in this lecture is called the infinite square well, and I'm going to do a simple kind of analysis based on the idea that the electron has a wavelength. But what I mean by the infinite square well is a potential energy, right? So you've got an electron, and anytime you have an electron interacting with something, it'll be through the potential energy. In this particular case, I set the potential energy to 0. In between or inside the well, in this range, we'll say x equals 0 to x equals L. So the length of the well is this length L. And we're dealing with a one-dimensional thing here. You could do this in 3 dimensions too, as it turns out, but we'll keep it simple with 1 dimension. Now the point is that if the electron has a wavelength, it's kind of like standing waves on a string. I can have a first harmonic that kind of would look like this. And the wavelength of this is twice the length of the well, or 2L. If I go up to the second harmonic, the next one I could fit in there with nodes at either end would be a wavelength equal to L. And I could keep going up to third, fourth, fifth types of harmonics. Third harmonic, you'd have 2/3 of the length of the electron wave, equaling a wavelength there. So 2L over 3 is the wavelength. And you can eventually come up with this formula, which is familiar from wave on a string physics, that the nth wavelength, or the nth sort of harmonic, or what I may call the nth state of the electron, is 2L over n, right? N is an integer, 1, 2, 3, 4. Now, if I want to calculate the kinetic energy of this electron, kinetic energy is 1/2 mv squared, or I could write it as p squared over 2m, right? P is m times v, and so this is the same as 1/2 mv squared. Plugging in my momentum wavelength relation, h bar k, this becomes h bar squared k squared over 2m, or h bar squared over 2m. Now I'm going to go ahead and plug in the 2 pi over lambda. So squaring that, I get 4 pi squared over lambda squared. But for this particular problem, the wavelength is given by this, 2L over n. And if I plug that in, I can actually calculate the kinetic energy of the electron in the well. Now it's all kinetic energy because my potential energy is 0 here. The fact that it's infinite on the sides kind of means it cannot get out of the well. It's stuck there. So the wave sort of has to go to 0 at the ends, and that's why I have nodes there. So what this tells me is the allowed energies of the electron, if it's a wave in this confined space, equal to n squared pi squared over L squared times h squared over 2m, or h bar squared over 2m. So what I end up getting are quantized energy levels. So the reason in atoms that you have energy levels that the electron can exist in is because it's a wave. It's kind of like a standing wave fitting in that confined space. One other thing before I write the Schrodinger equation, often we deal with atomic units for energy. Sometimes you'll deal with electron volts, but in atomic units, it kind of makes things simple. If I want to deal with electrons, I define the mass of the electron to equal 1, and I define h bar equal to 1. And this changes the units for everything, right? Units for velocity are now different than meters per second. The length unit is different. But what happens is it simplifies all of my formulas because h bar and mass of the electron is equal to 1. Now, if it's not the mass of the electron, it'll have some multiple of that fundamental electron mass. To convert from atomic units to electron volts or vice versa, you can use this conversion factor. And maybe we could talk more about atomic units later. But for now, let's go to some quantum physics. And one of the ideas of quantum physics is that you have operators and observables. And what do I mean by that? Well, for every observable thing in classical physics, let's say, like momentum or energy, there corresponds an operator in quantum physics. And as it turns out, the momentum operator, denoted by this little hat here, is negative IH bar times this gradient. Now, in 3 dimensions, what the gradient means is that you take partial derivatives in each direction, I hat, j hat, and k hat. You also can have a position operator, which we define just to be multiplication by x. I know we can talk more about operators later, but we can, from our momentum operator now, also define, and so I guess first I should say, by operator, I mean it operates on a function, right? So if you're in 1 dimension, your momentum will take a derivative of whatever function it's operating on. And I can then write down a kinetic energy operator too. P hat squared over 2m. Plugging in this for p hat, I get h bar squared over 2m p squared dx squared. Actually, there should be a negative sign in front here. But we also have not just kinetic energy operator, but a potential energy, which usually just depends on the position, right? In 1 dimension, for now, that's what we will do. The Schrodinger equation is kind of a total energy operator equation. If I take my total energy, kinetic plus potential, and operate on a wave function, it should return as what are called eigenvalues, the possible energies that this electron could exist at, right, or this quantum particle. And so what I mean by an eigenvalue equation is you got an operator, it operates on a function. If it gives you the eigenvalues, you will get the eigenvalue times the function itself. And so often what happens, we have to solve this Schrodinger equation. Kinetic energy is always kind of the same, right? It's always this derivative operator. Potential energy is where the different problems come in. If you dealt with an electron on a spring, for example, this would be 1/2 kx squared. But what we're going to do here is we're going to look at the same problem we just considered, the infinite square well. But before I do that, let's talk about what if you had a free particle where the potential energy was 0, right? So there's no potential energy. It's just a free particle, only kinetic energy. You would have this equation. I'm just multiplied by 2. So u is 0 multiplied by 2m over h bar squared. I get this. Derivative of the function, second derivative, equals 2me over h bar squared psi. And I'm going to define k, as it will turn out, it turns out to be the k in the wave number there, k squared times psi, the wave function. And this free particle, you can write the general solution in a couple different ways. You can write it as a sum of sine and cosine. Now you could also write it as e to the ikx plus b e to the minus ikx, because if you, I don't know if you've dealt with complex variables very often, but there's something called Euler's formula. And it turns out that really these e to the ikx functions are just a combination of sine and cosine. Sine theta plus I cosine theta is equal to e to the I theta. So the point is, I can write a general solution different ways for this free particle. And it's going to come up in our infinite square well, because inside that particular well, that particular potential function, u is equal to 0. Okay, so let's go to that case of our infinite potential well. Again, the potential is infinity if x is greater than or equal to L, or x is less than or equal to 0. So we've got these big infinite walls that the electron cannot get over, and it's 0 between 0 and L inside the well. So the solution in the well then, it's just the free particle solution, which I'll use a sine plus b cosine. Now the next step in any kind of problem like this is we've got to deal with boundary conditions. Right? When you have differential equations, you usually have either initial or boundary conditions. So our boundary conditions are going to occur at the edges of the well, where the wave function must equal 0. So the wave function at x equals 0 has to equal 0. If this is the solution, we can see that sine of 0, x equals 0, that's already 0. Cosine of 0 is 1. So this tells us that b has to equal 0. All right, so this part, to satisfy the boundary condition on the left side of the well, we must have only a sine of kx. On the right side of the well, psi at x equals L must equal 0. And so we must have that a sine KL is equal to 0, or just sine KL equals 0. And to satisfy that condition, this k must take only certain values, right? Kn must equal n pi over L. Now remembering our definition of k, that's equal to the square root of 2m times En. So we are going to get discrete energy levels once again, right? You can only satisfy this boundary condition for certain energies. And so if you go ahead and just solve for En, what do you get? You get this, which was exactly the energy levels we found just that from that simple model problem, or simple picture of the electron as a sort of a string with standing waves. So these are the possible energy levels of the infinite square problem. Now the infinite square well problem is kind of an artificial sort of potential. It isn't real. It's just kind of a mathematical problem that shows, though, how you can get discrete states out of this Schrodinger equation. In a real atom, you'll still get energy levels, discrete states, but you'll also get free levels, right? You'll also get free electrons that can actually move away from the atom. So you have a set of discrete states with certain energy levels, and then you also have what's called a continuum, continuous energies when the electron is above 0 energy, and it just has can move freely away. So the energy levels are labeled by this number n, 1, 2, 3, and it's often called the principal quantum number. It tells me the energy of the level, and it labels the bound states, bound possible states of this one-dimensional well in this case. Now, one last question that we need to answer our wave function we found is a sine of KL, right? Kn times L, where Kn was given by that only possible values we could to satisfy the boundary condition. But we haven't determined what this constant A is. And this leads us to the interpretation of the wave function, which is actually due, I believe, to Max Born. So sometimes this is called the Born interpretation of the wave function. And the interpretation is that the wave function itself is what we call a probability amplitude. If I square the wave function, I get the probability of finding the electron in a certain region of X, a certain space. Now I have to take this psi star side. The psi star is what's called the complex conjugate. When I have a complex function, the complex conjugate just changes all the i's into negative i's. And the reason for that is because it will give me a real number, which I need for a probability. I can't have a probability be a complex number. But often you'll see it as just psi squared dx. So again, the probability of finding the electron in the range x0 to x0 plus delta x, right, is the integral over the wave function. So it's sort of a probability density. Psi squared is a probability density. It's a probability per length in this case. And if I want the probability between, if for the electron to be somewhere, I have to integrate between the limits of where I'm looking. So let's say we integrated everywhere over all values of x. It must be true that the probability is equal to 1. We must find the electron somewhere. Now, when you integrate over, in this problem, over all values of x, well, the wave function 0 for x less than 0 and greater than L, right? I only have to go from 0 to L, but that integral must equal 1 so that the probability is equal to 1. The process of doing this is called normalization, because I can plug in my wave function, right? Kn is n pi over L. And what that will give me is a formula for this constant A. If I do the integral, it turns out to be L over 2 here. And I get that 1 is equal to A squared times L over 2. Solve for A, I get that A is the square root of 2 over L. Then I have what's called a normalized wave function. So my constant is determined by normalization. And this is the final wave function for any of the energy levels, right, labeled by n, the principal quantum number, of the infinite square well. Now, when you get to real atoms, the problem's quite similar, but of course the potential energy is different, and also it's three-dimensional instead of one-dimensional. But we can go ahead and maybe I can keep doing some lecture videos and we can continue to learn about that stuff as we go.